one takes 10 seconds. Okay. So, the moon. When I started to discuss with my colleagues what are you going to tell at the SpaceUP EU this year? And I said, oh, I'll talk about the moon. And they said, oh, the moon. I mean, everybody knows the story of the moon. But the moon is an interesting place because, and it's an interesting object because it teaches us two lessons. Never assume that you are totally right and that you can write your knowledge into a textbook. And the other lesson is a little bit more for natural science in general, is no matter what you read in textbooks, don't believe it and ask your own question. And that's why I call the talk The Moon Whisperers. Of course, everybody knows the movie The Horse Whisperer with Robert Redford, I believe. And the trick of the horse whisperer is he goes to the horse and listens what the horse says. So the horse says, oh, I'm sick, I have a lot of stomach ache, so he gives him better food and then the horse is fine again. So what I'm trying today with you is to let you be the moon whisperers, because you are the moon whisperers. You're not writing articles on the moon. You're asking questions about the moon. I think that's exactly what we need to do. And how do you ask questions to an object like the moon? Let me get my switch device going here real quick so I can switch to the next slide. Should be working in a second. Nope, it's not working, so I have to switch. Here. Okay, so how do you ask questions to the moon? You go there, and that's a picture of Apollo 17 mission to collect samples at the lunar surface. And this kind of interaction is actually what I mean by moon whisperer. So we go someplace, ask a question, and close the circle of scientific investigation. So we are having a question about the formation or the early days of the moon. So we're looking for minerals that would come out of an object that is in its early stages of development. You look for these minerals, of course you find something else. You're finding something else, you make a new hypothesis, you turn the loop back, ask new questions on that. And that's exactly what human exploration, also robotic exploration, allows us to do. So what's the history of this? 12 humans have set foot on the lunar surface. They spent a total of 7,500 hours roughly on the surface accumulated. They put 15 experiments on the lunar surface and they brought back 382 kilograms. The question we are asking today is, how did the moon form? And for that question they found the following preliminary answers. Of course the moon speaks its own language like the horses do. So we have to understand what the moon says, and we use chemical and physical models to understand the data or the language that comes back from the moon. And I've just listed the three most important things about the moon that came back from Apollo. Chemically, the moon is different from the Earth. It has no iron or very little iron on the surface. Physically, it's different from the Earth because it's very dry. And I don't mean there is a lake or a puddle or something. Dry means that the minerals have a very low fraction of hydrated minerals. Typically in the Earth mantle you find roughly 1 parts per million water, water in form of hydrated minerals. In the moon it's practically zero. But, surprise, surprise, isotopically, the moon is very similar to the Earth. And that's now creating a very diverse picture when you try to set up your hypothesis, because that's what the next step what you do is you get this information from the moon, and potentially without looking it up in some old dusty library books, you try to create your own picture in your head how the moon could have formed. So let's ask the moon, how did the moon form? there's the first theory that came up was capture. So you know who they trying to capture here? A giant squid. Giant squid with a sperm whale. So gravitational capture is a good idea. I mean, it's a huge object, the moon. So you know, being huge could be an indication of it was just captured in the gravitational by the gravitational field over the Earth. But that doesn't work out, because if it was captured, why does it have the identical isotopic composition? We know that Mars has a different isotopic composition. We know that Venus has a different isotopic composition. We know that the asteroids have a different isotopic composition. Why then, just by chance, should have an object that we capture into Earth has the same isotopic composition? So that leads to the next picture in our mind is, okay, so apparently the moon, because of its isotopic composition, is some part of the Earth. So why don't we think it is even been created by being flung off the Earth? So you get the idea is initially Earth was liquid, rotating quite quickly, and it just goes away. There is a little droplet that's flung off, and then the moon is, you know, after cooling down, the whole thing is created. However, that doesn't work out, because the initial rotational energy cannot go away that quickly. Even after 4 billion years, you need to see at least a little bit of that really fast rotation. And the other reason is we just found that the moon has no iron. If there is a homogeneous liquid and you flung off part of it, why should that part not have as many iron as the rest? So there must still be something different. And here again we have a other theory. It's called the coagulation theory, where basically you have the early Earth in the phase of formation, and around it is a debris field, and from that debris field, from the initial debris field, you get a new body. Well, that does explain the same isotopic composition, but it does not explain lack of iron on the moon, because if you build something from the same material, again, you should get the same result or a similar result. The leading theory until last year was the following. There was a time when the solar system was made of 20 planets. It's an estimate, nobody knows. Nobody made that movie, it's made in the computer. So there was a time where 20 planets around. And it was a violet time, because at that time all the planets were surrounded by debris disks, and those debris objects, they hit the surface of those planets very frequently. Asteroids were raining down from the skies every day, and there was no place actually where life could have formed, because it was so violent, so hot. There was no possibility for a foothold of life. So that was the Earth in say 4.6 billion years ago, just a couple of 10 million years after its initial formation. And then there was one of those 20 planets that was getting very close to the Earth. Let's call it Theia. And our proto-Earth, let's call her Gaia. And they came too close, and they hit each other. And what happened is you have that huge impact. And what that huge impact does, must have been a very bad day to be on the beach. What that huge impact does, it creates a debris disk. In this debris disk, you find very little water, because the energy of this huge impact just evaporates all the water. This, what it also does, it ejects only crust and mantle material from Gaia. Theia is completely destroyed. So it does explain the isotopic composition of the moon, because it's basically material that was just ejected from the Earth. And it explains also what two things we had, so water, iron. Because there is no part of the Earth core in that ejecta, and that's where the iron is. We get this. But last year, from this picture, we had that yesterday quickly, This is this orange soil that they found on Apollo 17, and here's a microscope picture of it. Those are glass beads, and inside those glass beads you see what people call pre-eruptive magma crystals. And those little things here, they are time capsules. They contain magma in the form before the eruption, and the eruption itself took place billions of years ago. And you can analyze that, and you compare that to what we know. And here we look at the water content. On the horizontal axis you have water content, on the vertical you have chlorine content. These are the moon rocks that we normally analyze. 0 water. The gray patch is what we have on Earth. From the Middle Ocean Ridge Basin, we get the gray patch. And the new things that are in those little crystals are the outline red ones. So, surprise, surprise, after many years of analyzing those rocks, suddenly the moon is not dry anymore. So the impact hypothesis doesn't work anymore. So we have to get a new one. And I showed that yesterday briefly. I don't believe in that theory, but it's so fun, so I have to show it again. There's the Earth core, and there's the Earth mantle, and between those there was so much fissile material that there was a natural nuclear explosion. Crazy, no? And that pushed out part of the mantle and the crust, and that formed the moon later on. And that would explain what we are seeing in this data, but it has all kinds of other problems. So message here is, when you're a horse whisperer and the horse tells you something, sometimes you can't really, you have to be open. And that's the same with the moon. Moon tells us something today that we asked the question like 60 years ago, 50 years ago, and we still don't really fully understand the answer. And that's why we have to do this. We have to keep asking the moon. We have to go there. We have to interact. We have to close the loop of scientific investigation. We cannot sit in our offices and make models, years end, without constraining parameters. We have to look at the moon rocks themselves and ask the question in situ. Like in Antarctica, we get the sample on the lab table. Lab table is there in the moon base. We find something new, next day we go out, ask a different question, get a different rock. That's what you have to do to find out how the moon formed, how terrestrial planets form, how the solar system evolves, all those things. If you want to really know, we have to do this. So finally, there is another reason why to go back to the moon. It's fun. Break up the volume.
May, when much to my surprise, a pair of bunny eyes. Oh, is this a neat way to travel? Isn't it great? I like to skip along, but me, boy.
Okay, I try one more slide. Oh, that's the last slide. Thank you.